thanks for the introduction, and I want to thank, of course, the organizers for this conference. It's been a nice conference and a nice long day. I'll extend it a little bit, hopefully not too long. I'm not sure how long, because when I was practicing the talk, every time I practiced it I got bored and stopped, so I don't really know how long it goes. Hopefully it's not too bad. Okay, so this, as the title says, I'm going to talk about semilattice polymorphisms on reflexive graphs. And this comes out of work with Pavel Hell, but we weren't really working on semilattice polymorphisms. We were working on some other problem with polymorphisms and using semilattice polymorphisms as a tool. And so I'll talk a bit about what we were working on to motivate it, but I'll glaze over maybe any results we got out of it. What's more interesting than any results we got out was this tool of semilattice polymorphisms, basically a bunch of observations we had about them. So from semilattice polymorphisms, we get a hierarchy of graph classes that turned out to generalize chordal graphs. We feel it's a new generalization of chordal graphs. At least we're trying to see where these classes of graphs match known classes of graphs. So I will start. Okay, so there. First, I want to spend a fair bit of time motivating it. So I'm going to talk about these polymorphisms, what they are, and try to convince you that maybe they're interesting, or at least explain why they're interesting to me. Then I'm going to say why we were looking at reflexive graphs. Then I'm going to start looking at see what a semilattice polymorphism is. And so those first three bits are basically background or motivation, and then I'll get into our characterization, these last two sections. So the basic characterization and then some refinements of it. So a little bit the talk is disconnected. There's maybe two parts, those first three sections. And the amount of material we carry through to the next two sections is minimal. But so if you want to sleep, either do it, take a half. If you want to lose track somewhere in the first half, then you can wake up again in the fourth section. Okay, so what's a polymorphism? Why do we care about them? So to talk about why we care about polymorphisms, I'm going to talk about this problem called the constraint satisfaction problem dichotomy conjecture. So this is something where I do a lot of my work, and polymorphisms are important here. So to do this, I have to give you some definitions. So here's a graph. We think a graph, I'm not going to think of this as a graph, I'm going to think of it as a relational structure. So a relational structure is just a set of vertices and then a finitary relation on the vertices. So a graph is a binary relation on the vertices. It's a special one, it's symmetric. But we're going to think about more general finitary relations on the vertices. So our graph maybe could have loops, or it could be directed. Or instead of a binary relation, perhaps we have a ternary relation, or even a unary relation. We might consider these. And for the most general relational structure, we could have all of these at the same time. So a relational structure is a bunch of vertices with all these different relations on it. But most of the time, just think of it as a graph. So for a relational structure, we define a problem called the CSP of H. Right? For some structure H, there's a constraint satisfaction problem based on H. And this is a framework for a computational task. Okay, so the basic framework, you have a computational problem. The idea is you're given an instance of the problem. You have a task you have a decision you have to make about that instance. You have to give a yes or no answer for that instance. And basically we care about the computational complexity of deciding yes or no for a given instance. So an instance of our problem is just going to be another graph or another relational structure. And the task we have to perform is deciding whether or not there's a homomorphism from the instance graph on the right to the fixed graph, H, on the left. So homomorphism, this was just defined a couple of talks ago, is just a vertex map, a mapping of vertices from the graph on the right to H that takes edges to edges. Right, so some examples of homomorphisms. An instance would be the triangle. Does this admit a homomorphism to H? Well, you can look and yeah, here's one. Right, here's a vertex mapping, it takes edges to edges. Another instance, maps to our target. So you can decide this, right? You can look at every possible mapping of the 4 vertices there, and you'll see that on any choice of 4 vertices, maybe you'll choose the same one twice, you're going to be taking some edge to a non-edge. So there's no homomorphism from K4 to H. So we care about the complexity of this problem. Given an instance, in terms of the size, the number of vertices of the instance, how long does it take us to decide this problem? And it's definitely, it's an MP problem. It's in MP. Right? So we care about whether it's, assuming that P and MP are different, then there's going to be these different classes within MP. We care, is it MP complete? Is it polynomial time solvable? Or does it come somewhere in between? Right? Because Ladner showed if P is not equal to MP, then P and MPC are different, and there's a whole bunch of complexity classes in between. Well, it turns out all the H we've investigated, all these relational structures where we know the complexity, it's either MP complete or it's polynomial time solvable. So Fetter and Vardy conjectured for any relational structure H, CSP is either polynomial time solvable or MP complete. Right? It doesn't, for some reason, it doesn't fall in these intermediate complexity classes. And so there's a lot of partial results towards this. So for certain classes of structures, it's been shown that it's not that we haven't found any intermediate problems. It's for big classes of problems, we know exactly where everything is, and it's either polynomial or MP complete. So for example, for graphs, we know it. For any structure with 2 vertices or 3 vertices, or this is just a lot of examples. So these last 3, sort of the techniques that are used in these are some algebraic techniques. Sort of one of the main ideas in this is that this result by Jevons, that the complexity of the CSP problem determined by H is determined completely by the set of polymorphisms of H. Right? So I haven't told you what a polymorphism is yet, but this is why we care about them. So if we find a set of polymorphisms of a relational structure, we know its complexity. Well, we should know its complexity. So what are polymorphisms? Well, there's a couple ways to look at them. A polymorphism is just now a finite area operation on H that preserves relations. So if we're looking at a graph, so a finite area operation phi just takes d tuples to vertices. So you take 2 different, for every d tuple you have an image. And to say that it preserves relations is if each column is in the relation. So if each ui, vi is an edge, well then the image has to be an edge. So this is what it means to be compatible with relations. So another way of looking at this is a polymorphism is a homomorphism of the categorical product of the graph down onto the graph. So I'll define categorical product just by example. So for graphs, it's the graph whose vertices are the categorical product of the vertex sets of the original graph, and an edge, or an edge is in the graph if both of its projections are in the graph. Right? So if this projection and this projection are in the graph. So the square of a triangle looks like that. Right. So yeah, and so the polymorphism is just a homomorphism of this back down onto the triangle. Right, so let's look at some examples of polymorphisms. Okay, so we're going to look at polymorphisms of K2, simple examples. So this is K2 to the power 3. So we just want to look at now 3-area polymorphisms. And the way I'm going to represent them is just I'm going to put colors on the vertices of the target, and I'll represent my vertex map by coloring the vertices with where I'm going to map them. So here is a polymorphism. It's just a mapping of the vertices. All these blue ones go to the blue one here, and it takes edges to edges. And here's another, right? And here's another. And so there's a lot of them. Here there's 16. Generally, we'll say this, so we call these vertices diagonals because all the entries are the same. And so we'll always assume that the diagonal one goes to its entry, right? So I'll always assume that this is blue and this is red. And so if you know anything about polymorphisms, I'm saying I'm assuming all polymorphisms are idempotent. So there's 8 polymorphisms here. But if you notice this the previous one, I think, this last one is what we call a projection. So it's just taking, every vertex it's projecting it onto its second coordinate. Right? So the second coordinate completely determines where we take the vertex. So a more interesting example is maybe, I'm going to look at the two-area polymorphisms of K3. So here I'm looking at homomorphisms from that product down onto K3. And here's one, the projection. So one thing we'll note is a projection is always a polymorphism. Right? Here's another. And there are no others after this. So these are the only polymorphisms of K3. That takes a bit of checking, but not too much. And so actually, of all arities, the only polymorphisms are projections. And this is an interesting property most graphs have asymptotically. Almost all graphs have this property. And it's interesting because Jeevan shows that if the only polymorphisms are projections, then the CSP problem is NP complete. So I'm going to define a polymorphism that's very far from a projection, in a way. Right? So this is, if a polymorphism satisfies this identity, we call it a weak near unanimity polymorphism. And you can see this is definitely not a projection, because we look at the value of phi on, these should all be commas, I think. But they are commas. Yeah. Okay. So it's a polymorphism is a weak near unanimity if for any pair of vertices, if the entries in the tuple are almost all x, only one's a y, it doesn't matter the order. Right? And so if you try to, if you have this identity, you're definitely not a projection in any onto any index, because here we have, in any index, we have y occurring in that index and getting the same image as a tuple with x occurring in that index. Right, so these, in a way, are anti-projections. And so Jeevans with Bulatov and Kroken showed that CSP is NP complete. Okay, they didn't show this, but as a result of what they showed and what Murati and Mackenzie showed, we have that CSP H is NP complete if H admits no weak near unanimity polymorphisms and is otherwise, it's conjecture. Sorry. So what we know is CSP is NP complete if it admits no weak near unanimity polymorphisms. And they conjecture that it's otherwise polynomial time solvable. Okay, so here's just the same definition of weak near unanimity polymorphisms. And so we have all possible finitary relations. And when you're looking at the set of relations that are a polymorphism of a structure, if they're all projections, the structure is NP complete. If all the polymorphisms fall in here, the structure is NP complete. But the conjecture is if there's even one that's in this weak near unanimity set, then the structure should be polynomial time solvable. So we don't know that yet, but if we change the definition a little bit, there's a special kind of weak near unanimity polymorphism, which is called the near unanimity one. And it just has this added condition that we know the target. We know the image for these tuples. Well, if we have a polymorphism like this, then the CSP is polynomial time solvable. So we can, for these special weak near unanimity polymorphisms, we can show that. And there's other weak near unanimity polymorphisms, the totally symmetric one. So here's a polymorphism that it doesn't care about the order of the entries. So it just looks at the set of entries as a set, so it doesn't care about repetition either. And if your entries, if you have the same entries as a set, then you have the same image. So if you have a polymorphism like that, then we can show that, well, we can show, Fetter and Barty did both of these. You can show that CSP is polynomial time solvable. And so a lot of these sort of partial results towards the big conjecture are people show for special graph classes, if you have a weak near unanimity, for some graph classes, if you have a weak near unanimity polymorphism, then you necessarily have a near unanimity polymorphism. Or other results have said, well, all weak near unanimity polymorphisms are sort of a hybrid of near unanimity and TSI, and so they can take the algorithms associated with both of these, the polynomial time algorithms, sort of make a hybrid of the algorithms and then get an algorithm saying, here's the polynomial time algorithm to decide whether a graph maps to H. Right, so that's what I want to say about that, I think. Now I want to look at specializing. Now I'm not going to talk about all relational structures, merely reflexive graphs. So what's a reflexive graph? Well, here's a graph. And the reflexive version of this graph is just adding all loops. So the CSP problem here now becomes trivial, because as soon as I have a loop on my target, I can map all vertices to that target. So it sounds like it's not going to be interesting. So we want to make this non-trivial. So we have to add something to this reflexive graph. And what we add are a bunch of unary relations. Right? There's 5 different unary relations, each a different relation. And so now our instance is also going to have elements in these relations. Perhaps it has these two. So maybe you can't see the yellow. This vertex is in the yellow relation. There's a vertex in the black unary relation. And so for a homomorphism, they have to map. We have to preserve these relations. And so there isn't, you can see this instance now doesn't have a homomorphism to the target, because this edge is mapped to a non-edge. So now the problem is no longer trivial. Right? So when I'm talking about reflexive graphs, this is what I'm assuming. I'll just draw the graph, but this is what I mean. So it has these loops. It has all the one-element unary relations. And I'm also assuming it's connected. That's a trivial reduction. Okay, so why are we interested in reflexive graphs? Well, the dichotomy has been done for irreflexive graphs for quite a while. And it's been shown that, Fetter and Barty again showed that if we know it for, when I say the dichotomy, I mean this conjecture, I said earlier in the talk. They show that if we know it for digraphs, it's equivalent to knowing it for all relational structures. And there's a feeling that reflexive graphs are slightly harder than irreflexive graphs. Irreflexive is just simple graphs, and but it has some of the complications that we can't deal with. So there's been some results done on it. So you can generalize the idea of CSP to what's called min-hom. So it's basically you're looking for a homomorphism, but you put weights on certain edges and certain mappings, and so you want to find the smallest, the least weight homomorphism. So it's a generalization of the homomorphism problem. And so there's dichotomy for that. Right? So easy cases of this, of course, are easy cases for us, but the NP-complete cases of that might become easy when we're only looking at CSP. And there's been a fair bit of work on just the near unanimity polymorphisms on reflexive graphs. So now my polymorphism oval has fallen over, but still, so where we are. We care about the weak near unanimity polymorphisms on a structure, and those near unanimity ones have been characterized. And this is by Roosevelt and Tardif. And in their characterization, they showed that any graph that has a weak near unanimity polymorphism has totally symmetric idempotent polymorphisms of every arity. So in our original picture, these were sort of different, different potatoes. Now, NU is a subpotato of TSI. Right, so then we think NU has been well characterized. The next step is maybe TSI. Right. So what we were looking at, these are our goals from lofty to less lofty. We would like to, ideally, we want to prove this conjecture for reflexive graphs. If we can't do that, well, let's at least characterize the reflexive graphs that have near unanimity. Failing that, TSI, and failing that, so it's slightly stronger having TSI of all arities. Because if you have a TSI of arity 4, you don't necessarily have one of arity 3. So this was our motivation. And so that's that part of the talk. Now I just want to talk about semilattice polymorphism. So this is a type of totally symmetric idempotent polymorphism. So we were looking at TSI polymorphisms. And one of the big problems with them is when you try to get small examples on small graphs, it's a bit ugly to define them. Right? So we wanted to get a feeling for certain graphs that had totally symmetric idempotent polymorphisms, but not near unanimity ones, so we were playing with small examples. And so this is an example of a fairly small, quite symmetric graph, and I had to go through some work. I mean, it's trivial, but it's sort of a lot of writing to define a totally symmetric idempotent polymorphism on this. And it's a fair bit of work to actually show that it's a polymorphism. Right? First you have to define the function, then you have to show it has the right properties. So this isn't always the case though. There are certain totally symmetric idempotent polymorphisms that are easy to define. And that brings us to a semilattice polymorphism. So a semilattice polymorphism is a two-ary polymorphism that is idempotent, associative, and commutative. Right? And so we call that semilattice because it defines partial ordering by this equation, which is actually a meet semilattice. Right? And because it's a meet, and as the meet semilattice, the polymorphism is actually the meet. Right? So the image of two vertices is going to be their meet in the semilattice, and so I'm going to denote the polymorphism. Instead of using phi, I'm going to use a wedge. I'll call that wedge or meet, usually wedge, but yeah, it's the meet. Okay, so given a graph now, I want to define a semilattice polymorphism. That's easy. Right? I just put a semilattice on it, and this now, where does 11 and 7 go? Well, it goes to the meet of 11 and 7. So I just have to draw the graph. And the nice thing is, when you have a semilattice polymorphism, it actually defines a totally symmetric idempotent polymorphism of every arity, just by taking the set and just looking at the wedges that are associative, so I can write it this way. I just look at the wedge of all the entries. So if I have a three-ary totally symmetric idempotent, and there's the image of those three vertices. Right. So this is kind of why we were working with semilattice polymorphisms. They're just easy to draw totally symmetric idempotent polymorphisms. And so you sort of notice this. If you have a near unanimity, and sometimes I accidentally put an F on the end of near unanimity, that's because sometimes it's called the near unanimity function. Ignore that. So if you have a near unanimity function, then you have TSI of all arity. If you have a semilattice polymorphism, you have TSI of all arity. Are near unanimity and semilattice, are the graphs that admit these the same? So this is a question that comes up. And likely it's not true, but there were no examples of that. Right. So now I want to get to our classification. So we're working with these semilattice polymorphisms. And it's nice. So because you're working with semilattice polymorphisms, you get examples of graphs with totally symmetric idempotent polymorphisms. You simply pick a bunch of vertices, put a semilattice on it, and then throw a bunch of edges on top. And there you have a graph, and we have a semilattice function defined on that graph. Oh, we got to check that it's a polymorphism. So what does it mean to be a polymorphism? Well, you have to satisfy, this is our homomorphism. The idea is you have to preserve, you have to be compatible with edges. So you have to satisfy this, right? And graphically that looks like this, right? So what am I saying here? The red vertices are my U prime, V prime. The blue vertices are the wedges of the ones they look to be the wedges of. Those black edges are the edges represented here. And so if you have sort of this situation, well, sorry, that disappeared. Then you necessarily have the edge between the wedges. Right? So you have this kind of graphical rule, and you can use this to decide whether or not this is a polymorphism. You just put those red vertices on the graph and see, oh, well, it wasn't a polymorphism, so I have to have that edge there. Maybe I'll put them here. Give you a second to see what's going on. What edge does this put there? You have to have that edge there. When I put these vertices here, well, I see I had to have that edge there. And you can do this on sort of all sets of 4 vertices. And then here now, with the edges I started with, now I get a graph that actually has a semilattice polymorphism. And the polymorphism I sort of defined almost randomly. This identity is a bit hard to work with, though. It's hard to look at that graph and say, well, oh, I'm missing this edge here. So we have sort of consequential identities. Just in certain cases, identifying some of those blue vertices, putting them, ordering them with respect to each other. I have these special versions of the identities, and I can put them together. So how do I read these? I read these as if these are my ordering, so these blue things, these fat blue things are just my ordering. If I have those black edges, so those ones on top or that one on top, then I necessarily have these blue edges. Okay. And these are quite visual. These are easy to, when you have the thing drawn out the way I had it, it's easy to see that these are satisfied. But they're not always sufficient. So these identities are consequences of that original homomorphism identity, but they're not sufficient. They don't imply it. But if we do put a couple restrictions on our semilattice, then they will imply it. Right? So here I gave certain identities, I have names, give names, so I have my V identity and my X underbar identity. So I'm going to put some restrictions on semilattice polymorphisms. I'll say it is embedded if every Hass edge, so that's the order edges, the blue edges, is also a graph edge. I didn't have that before. I say it's tree if the Hass edges induce a tree. So from the previous slide, I removed one edge there. I say it's skeletal if all graph edges go between comparable vertices. Right? So before, I had edges that were between incomparable vertices. It's skeletal if all graph edges go between comparable vertices. So these gives me stronger ideas of semilattice polymorphisms. And so I have these strengthenings of the idea of a semilattice polymorphism. And I can put these conditions together, right? So I can have a semilattice polymorphism that is a skeletal tree polymorphism. And it's not too hard. Using this identity, you see that if you're embedded and a tree, then you have to be skeletal. Because if you're embedded in if you're embedded in skeletal, then you have to be a tree. Because if you're not a tree, then you have some peak like that, and then if you're embedded, then you have these edges, and so that edge has to be there. So you can't be skeletal. So our hierarchy sort of collapses a little bit. And apart from that, you can have polymorphisms on graphs that are embedded but not skeletal, or embedded tree but not skeletal, or skeletal tree not embedded. So apart from that, these are all different kinds of polymorphisms. But we don't really care about them as polymorphisms. We care about the classes of graphs that have such polymorphisms. And then things start collapsing again. So the first thing you can see, you'll see, is that if H has a skeletal semilattice polymorphism, then it has an embedded skeletal tree semilattice polymorphism. So our chart there collapses a bit and becomes a bit easier. And this, maybe it's not obvious to see this. It isn't obvious, but it becomes pretty obvious when you make a couple observations. And the first one is that that's equivalent to being chordal. So maybe I don't want to show you the details of this because then it'll reveal how obvious it is, maybe. But a chordal graph is just a graph. We saw the definition of that. Any induced cycle of length 4 or longer has a shortcut across it, a chord across it. And so that is trivial to show that if you're skeletal, then if you admit a skeletal semilattice polymorphism, then you're chordal. And not too bad if you know a little bit about chordal graphs. The perfect elimination ordering it sort of expands to an embedded skeletal tree semilattice ordering in a nice way. So you get this identity, which actually took us we were trying to show some of these identities without using chordal, and they're quite hard to show, but then when you make these observations, it's sometimes trivial. Okay, and the special case is if you have this embedded skeletal tree, but it's just a path, but then you're an interval graph. So these are semilattice polymorphisms. We were looking on reflexive graphs. They're defining classes of graphs that are known as irreflexive graphs, right? Interval graphs, chordal graphs. Well, I guess we can look at those as reflexive graphs if we change the idea of what an intersection is. But okay, right. Okay, so we have this, and then one last thing was a bit harder to show. You can show that if A is a polymorphism, then it admits an embedded tree semilattice polymorphism. So the basic idea is if you have a tree polymorphism that isn't embedded, you can make local changes and embed it. Right, so we actually get a true hierarchy here of semilattice polymorphisms. Are they different? Oh, yeah, and so the interesting thing about some of these lower, stronger semilattice polymorphisms is these identities are enough. Right? So when we draw it out, these identities are sufficient to show that it's a polymorphism. And in this hierarchy, we know that there are chordal graphs that aren't interval. It's not bad to see here's an embedded tree, a graph of an embedded tree polymorphism that's not chordal, so it's not skeletal. Here is an example of something that has an embedded semilattice polymorphism, but not an embedded tree one. It's a bit hard to show that it doesn't have the embedded tree one, but it's messy, not hard. Here's an example of something that has, well, it admits a totally symmetric idempotent polymorphism, but not a semilattice. It admits TSI of all arities, but not semilattice. And that's something we didn't know existed, and we were interested in that. And so using sort of some of these techniques with the identities, it became still a bit messy, but we were able to show that it doesn't have semilattice. And the next corollary we got of that is that the classes of graphs that admit semilattice and new unanimity polymorphisms aren't equal. And maybe I'll skip the details of that too, but this is just, at the end, if I have time, maybe I'll go over it. It's a really nice proof. Okay, we don't know this. We don't know if any graph that has a semilattice polymorphism, perhaps it has an embedded one. At times I believed that, I thought I could prove it, but I can't quite get there. So I kind of feel it's true. I kind of feel that these are the same classes, but I can't show it. So another thing we were interested in, these path semilattice polymorphisms, the skeletal semilattice polymorphisms are known classes of graphs. Embedded tree properly generalizes chordal graphs. We know a lot of classes of graphs that generalize chordal graphs. Is embedded tree one of those? If you're interested. Embedded. And still, embedded tree is nice because it just has these graphical identities. So it's sort of a nice characterization. So Pavel, we were asking these questions, and he sort of had a candidate for possible embedded tree for a known class of graphs that correspond with embedded tree polymorphisms. So these are chordal reducible graphs, and this is a graph he and Feder sort of came up with, this class of graphs. And I haven't been able to get out of him why. He's very secretive of that somehow. But here's the definition, and it's kind of an ugly definition. So I'm going to define what it is for a graph to be chordal reducible. So given a graph H, what you do is you take its clique graph. So for every maximal clique, you put a vertex. Right? And if two maximal cliques intersect, we're going to put an edge between the corresponding vertices. Right? So here's our clique graph. Now we take the incidence of the original graph and its clique graph. So these three vertices were in the maximal clique corresponding to the red vertex, so we put edges between them. So we do that for all the cliques. And now if we can remove edges from our original graph, keeping it connected, such that this thing is chordal, then we call the graph chordal reducible. So it's not a really intuitive definition to me, and it's sort of don't know where it came from. So I stand by the statement that it's not intuitive. So we thought it would be nice if it fell into our hierarchy. So some things I know about these chordal reducible graphs is they generalize chordal graphs, right? But they also include graphs with universal vertex. So these are both classes of graphs that have near unanimity functions, and so when they were trying to characterize the graphs with near unanimity polymorphisms, this graph class was interesting. They actually showed that chordal reducible graphs have near unanimity polymorphisms of similarity. Some questions about them. We don't know. So chordal graphs, there's polynomial times algorithms to recognize those. It's nice, but this doesn't extend to chordal reducible graphs yet. But they feel close enough to chordal graphs that perhaps there should be one. Where's that algorithm? A question that came up. So LaRose asked this. When he saw these graphs, he thought, so chordal graphs all have all graphs that admit a 3 near unanimity polymorphism are chordal, but not all. But but there's some that are not chordal reducible. Yeah. But his conjecture was kind of that all graphs with the 4 near unanimity polymorphism are chordal reducible. So this is something that we were kind of interested in, but not super interested in. This is what we were mostly interested in. But we got an answer towards this. And we don't know anything about this. So let's actually sort of look at how these chordal reducible graphs fit into the hierarchy. So you can see that a chordal reducible graph has an embedded tree polymorphism. And the way you do this is you take this, here's our original graph, and then we have these cliques. They're hard to see there, but there's vertices for the cliques. And the way I've drawn it, perhaps they don't actually correspond to cliques. I made a random graph and threw some clique vertices in. But so there's vertices there that are clique vertices. And the point is, if you have a graph such that this clique graph is chordal, well then it has skeletal tree embedding. That's skeletal embedded tree polymorphism. Right? And so then you throw away your clique vertices, and with a bit of work you can show that what remains in the original graph, the skeletal polymorphism on the certificate with the clique vertices defines a skeletal semilattice on the original graph. It stays connected, so it's going to be an embedded skeletal tree polymorphism on the original graph. Oh, this isn't the original graph. There were some edges that we removed. So the idea is when you put an edge in there, then you can sort of argue that all the edges that you need in the graph were actually there. So if the graph actually had this edge, well then those two vertices are in some clique together. Right? But they're incomparable, and all edges to the clique are still in the graph, so their clique had to be at least below their join. So it had to be here or here. And so because we had this x underbar property, well, all vertices between them and the clique they're in are also adjacent to that clique. And because our skeletal polymorphism was embedded, this vertex is always also adjacent to that clique. So all these graph vertices were actually adjacent. And so we get our identity. We get our V identity and our x underbar identity. And so in this way you actually you can show that the original graph had an embedded tree polymorphism. And we were trying to show that if you have an embedded tree polymorphism, then you're chordal reducible. We wanted that these classes were the same. But from this proof, this hand-waved proof, when you go through it, you actually get a stronger identity than these ones here. Sorry. You get this identity on V's. Okay, so I'm missing some edges here. This one should be there. What we actually get is, in a situation like this, where we have these comparable compared vertices and an edge across the top, all edges are in between there. And the degenerate version of that is this. So we can weaken this, and we have sort of two different strengthenings of the idea of an embedded tree polymorphism. We have what I'm calling a clique V embedded tree polymorphism and an interval clique V embedded tree polymorphism. So these are polymorphisms that when you can draw the graph, the picture of the polymorphism with the edges just has to satisfy these graphical identities. And we can show that if you have this type of polymorphism, then you're chordal reducible. If you're chordal reducible, you have this type of polymorphism. And I feel chordal reducible actually corresponds with this. That's something I'd like to show. Okay. So this is basically our hierarchy. We had the bigger hierarchy, and this is sort of, we focused in and sort of defined these less natural ideas, I feel, but if they correspond with chordal reducible, then they're nice. Semilattice polymorphisms. And so the ideas we came up with here is seeing this, using this fact that if you're chordal reducible, you imply clique V embedded tree. We were able to get an example of a graph that has a 4 near unanimity polymorphism, but no clique V embedded tree polymorphism, so isn't chordal reducible. So these techniques allowed us to answer something that maybe not asked formally was, well, someone that knows things thought might be true. So I'm not going to say it was a conjecture, but it was something that he was curious about. Okay, so right, so this is basically an outline of what we've done. We defined this hierarchy of graph classes, and it properly generalizes chordal. It allowed us to show that for reflexive graphs, the class of graphs admitting semilattice polymorphisms is not equal to the class of graphs admitting near unanimity functions, and it allowed us to show this last example. So now what we're interested in, so this isn't what we were looking at, this hierarchy, it sort of just arose, but it became quite interesting to us. So we would like to know, where does chordal reducible fit into that hierarchy? That other question I asked, does semilattice imply that there's a embedded semilattice? And one thing we feel we should be able to get out of this is polynomial time algorithms for these things higher up the hierarchy. There's a nice polynomial time algorithm for chordal graphs. We feel we should get an algorithm for getting higher up the hierarchy. And why we feel this is, there are nice polynomial algorithms for recognizing graphs that admit near unanimity functions, but nothing known about TSI. It's known it's hard to recognize weak near unanimity. That was one of my results. Okay. And one thing that we're really missing from this theory, if it's going to be called a theory at all, it's just a bunch of observations, is it's hard for me to show something doesn't have a semilattice polymorphism without showing at the same time that it doesn't have a totally symmetric idempotent polymorphism. There's ideas of obstructions to totally symmetric idempotent polymorphisms. And somehow we feel we have to refine that to get something that allows a TSI but still obstructs a semilattice. And we haven't got the right idea for that. So that's something I would really like to see. And I think I'll stop there. I had that proof that I said I liked, but that's good enough.